So this is our lesson on mechanical energy. So we just finished learning about regular energy and a little bit more about force diagrams and the way to kind of break down those components. Now with mechanical energy, we're going to move into the study of mechanics, so kind of putting some more stuff together. And our study of mechanics specifically is the study of kinematics. Kinematics, statics, and dynamics. So we're kind of putting all of our stuff together here of why something moves and how it moves, and it should be like just a little bit further of extension, because remember, kinematics is the study of motion. Statics is our study of forces in equilibrium. And our dynamics is the study of motion that results from non-zero forces. So I'm going to kind of shorthand that to motion with forces. And you don't have to put that if you know that or if you understand that. And our mechanical energy is the sum of potential and kinetic. So we learned a little bit about potential energy and kinetic energy. We didn't really get into it because I wanted to focus more on other things. But it's the sum of those energies. And what we kind of looked at before is we studied like the changes of these energies. Now, work can also cause a change in this at any time. Like if we think about how an engine increases the thrust of airplane, so it increases the speed and changes the kinetic and changes the height, so the gravitational potential energy, we're going to have a new theorem to deal with in order to kind of understand how these things work together. And what we're going to bring together is this idea that work is equal to the change in, I got that backwards. We write it differently. The change in the kinetic energy plus the change in the potential energy. So that's the whole theorem. It states that the work done on a system is equal to the sum of all of the changes, which should make sense. This is literally just an expansion of our last formula. And we'll get into how we can calculate our mechanical energy, but also remember that this can be broken down. We used to have it written as the net force. So if we have the change in kinetic energy, it can also be written as your mass acceleration and then worrying about your cos theta and the change in the displacement, because we used to write this just as F, but that F can also be written as mass and acceleration. So we should see how these things affect together. We're going to use our work energy theorem right away in this example here. So it says a block is moved up a frictionless, so it's moving upwards, inclined plane, and it's frictionless, that's important, parallel to the plane. Okay? At the foot of the incline, the block is moving 1 meter per second, so at the very base of it. This block has a mass of 1.2 kilos, and we have some heights in here. What is the work done on this block as it moves up the incline? Okay, so we have all our wonderful variables, and we have our new formula here. This W is equal to the change in the kinetic energy plus the change in the potential energy. We know that this EK can be written a few different ways. It can be written with worrying about cos theta. We know it can also be written as mv squared. We also write it a little bit differently, where we have it all over like this. And that's just a preference. of how you want to write it. And then this EP can also be written, because that's your potential energy, is mg delta H. So you have all these different ways to write the same equation. So we're going to change. We have our change in kinetic energy. We have a change from the top to the bottom. So we have two different things to deal with here. So we have our EK2 minus EK1. So that changed here, plus this is going to change to our mg delta H. Awesome. Now, if we look at this, this is the second part, because this tells us that this is the initial velocity, and then it's moving at this velocity. So this is EK2. So if we have EK2, mass velocity squared, this is just us still setting up the equation. And if you understand this and you've already zipped past this step, that's great. Everybody's understanding's at a different spot. Plus mg delta H. Now let's plug in our values. So this tells us the mass, this tells us that the velocities. So we're going to go our mass, which is, it's a 1.2 kilo block, multiplied by your velocity squared, so 1 squared, all divided by 2, minus 1.2 kilograms, multiplied by 4 squared, close brackets, plus 1.20 kilograms multiplied by 9.81 meters per second squared. And then what are we missing there? The change in height. Oh, I think I can actually just move this over. Let me try and do that. Yeah, select my annotations. Select less annotations. There we go. Multiplied by the change in height, which is 0.850 because you start at rest, and move all the way up. Now let's slam some numbers into our calculator. So this is going to end up being 9.60 joules minus 0.60 joules, close those brackets, plus 10.01 joules to give us 19.0 joules. So this is the work caused to push it up. And this tells us that it's 19 joules of work, and then we had 9 joules of kinetic energy. Because that's what this calculated. This ended up calculating the work, and I should put my variables in a little bit longer. This tells us the change in the kinetic energy, and this tells us the change in the potential energy. So our EK, the kinetic energy, was equal to 9. And then our potential energy was equal to, rounded, 10.0. Now, the next thing that we're going to do is we have our calculations of mechanical energy. We are going to use this formula, EM, mechanical energy, is equal to the kinetic energy plus the potential energy. So it's just another kind of derivative, and it's just we're just finding the total of the kinetic energy and all forms of potential energy. So we have a cannonball is fired from Earth's surface at the peak of its trajectory. That's important. It has a horizontal speed of 160 meters per second and is 1.2 times 10^3 meters above the ground. With reference to the ground, what is the mechanical energy of the cannonball at the highest point of its trajectory if the mass of the cannonball is 5.2 kilos? So let's sketch this. We have, this is my cannon. Then I have a parabola, because we know that all shapes have a parabola when they're fired like that from our kinetic energy. Then we know that the peak here is going to be the highest, so that is our h. We also know that we have a second velocity of 160 meters per second, so at the peak, 106, oh, I messed it up. Let's try that again. 160 meters per second, and this height is equal to 1.20 times 10 to the 3 meters above the ground. And then we have our h, we have gravity, and we have a mass. And what did I say else? We had a mass. Velocity and height. Okay, and we want to find the total energy of the cannonball, so we're looking for that EM at the peak there. So at the top of its trajectory, this cannonball has kinetic energy due to horizontal motion and EP because of its height above the ground. So we're going to use our formula. EM is equal to EK plus EP. We know that EK equals mass velocity squared divided by 2 plus mg delta h. Okay, so our mass is 5.2. Our velocity is 160. And because we're looking at this specific instance of this situation, I don't have to worry about an initial velocity and a final velocity. 2 plus mass, gravity, and the change in height, because the height we originally started at, we're not worrying about this. We're talking about this specific instant relative to the ground. If I said that this was at 2 meters, then this height would have changed, but it doesn't say that. We're just not paying attention to the height of the cannon. We're saying in relative to the ground, what is this? So that kind of saves us, again, a little bit more math. Okay, so then we calculate this out. Our kinetic energy is going to be 6.656, and I have a few extra sig figs here because it's an intermediate calculation. 6.121 times 10 to the 4 joules. So then if I look at this, everything is to 3. This one's 2, so we'll have to take it down to 2, which means that this is going to give us, what is that? Add it together there. Let me grab my calculator. 6.56. So it should be 1.3 times 10 to the 1, 2, 3, 4, 5 joules. And again, the total energy at the top of the parabola is 1.3 times 10 to the 5 joules, but we also know that we have our kinetic energy and we have our potential energy, and it's important to note that this is positive because the cannonball is higher than the reference point. So think about that while you're doing the questions, that if it's where it is in relation to the reference point. But that's it. You guys should be good to go. If you have any questions, please let me know.